Hey, this is Mr. Aiden. We're going to be calculating higher order derivatives today in calculus, so let's get to it. If you remember back to physics, hopefully you remember that when we had a position time graph, a dt graph, that we can take the slope, or what is our term for a slope in mathematics as well as physics, is we can take the derivative, can't we? And that derivative will end up giving us the velocity time graph. And if we have a velocity time graph and we want to find the acceleration time graph, we're going to take the slope or the derivative. Okay, and so this is something we're going to get into later in the applications of derivatives, is when we have a position time graph, like if you remember, we have x as a function of t. If we take d over dt of that, d over dt of this function, we get dx over dt, or what we call vt, a velocity time graph. And if we take the second derivative of this x function, this second derivative of the x function, what we call d squared x over dt squared, that's the first derivative of the velocity function, d over dt, and that ends up giving me my acceleration time graph. And so this is something that we've done from 9th grade on. We're just going to take the slope, but in this case, we're able to do more than just kind of little kind of functions. We can do any function possible because we can take the derivative of it. Okay, and so you can see our first function here. Let's take an example. We have a guy that's on a cliff. Let's say he's 15 meters off the ground. Ironically, his name is Cliff, and he is going to throw a rock, not Dwayne Johnson, something else, straight down, and he throws it with a velocity, an initial velocity of 18 meters per second. And so he kind of throws this bad boy down off this 15-meter high cliff, and this is the function showing that. The y value is my height, okay, so y is really my height, and my x value is really my time. And you can see I have a position time function right here. And so how am I going to find the velocity is I'm going to take d over dx of everything here to find my velocity function. And I'm going to take what we call the first derivative. So my dy over dx, or what I would consider my, hopefully you can see the implicit differentiation, that my slope of my tangent line is equal to the power rule, the d over dx of all this. So 5 times 2 is 10x plus 8. And so this is my velocity function, which means if I want to know at 2 seconds how fast this rock is going, I can just put a 2 in for x, and I end up getting the velocity. Well, if I wanted to find the acceleration of this rock, well, what I do is I'm going to find the derivative again, which is the second derivative. If I did this value right here, it would be the second derivative, d squared y over dx squared right here. And so I would take the derivative of this guy, which is d squared y over dx squared, the second derivative. And what's the second derivative of 10x plus 8? It's 10. And what do you know 10 is? It's the acceleration of gravity, which is 9.8 meters per second squared, but 10, and you can see how the acceleration of this function is equal to 10, the velocity of this function is equal to 10x plus 8, and you can see how all of my equations, if you go back to your physics equations from 9th grade, or your AP physics equations in 11th or 12th grade, they will coincide with our thinking here on higher order derivatives. Okay, so let's take an example. We're going to calculate the second derivative of this function right here. And so this function is really 5x to the negative 2. And so when I find dy over dx, I'm going to do the power rule. I get negative 10x to the negative 3, or negative 10 over x cubed right there. Well, if I want to take the second derivative, that's d squared y over dx squared. And you might say, Aiden, how did they come up with this weird thinking? Well, if we have y, and again, I'm going on a little tangent over here. So the first derivative is dy over dx, or you could say d over dx times y, right? And so the second derivative would be my d over dx of my d over dx y hopefully you can see how kind of we have a d squared y up top, we have a dx squared on the bottom. That's kind of how it works out. So let's get back to this example. Let's get off my derivative or tangent and get back onto my problem. So now I'm going to take the second derivative. So I'm going to take this derivative, this negative 10x to the negative 3. I'm going to multiply it out, do the power rule, so 30x to the negative 4, or you could rearrange 30 over x to the 4th, and that is the second derivative. Sometimes it gets a little bit more complex, okay, you can see right here, I have kind of implicit differentiation working in here. So I'm going to take the second derivative of this function. And so you can see, again, we're going to have to do some implicit differentiation here. Okay, so I'm going to take the d over dx of everything. So I'm going to get 2y dy over dx minus 2x dx over dx equals 0 right there. Which means, what can I say here is I know that the dy over dx, the first derivative, equals 2x divided by 2y, or x divided by y. I hope you can see that. So that's the first derivative of my function. Now let's take a look at the second derivative. So I'm going to now do the derivative of this function right here. Okay, and so when I take the derivative of this function, which is obviously the second derivative of the original function, I'm going to get d squared y over dx squared, that's the second derivative, is equal to, and I'm going to use the quotient rule. I could rearrange this, use the power rule. I could do a bunch of, the product rule. I'm going to do let's do the product rule. Okay, you can do it either way. So what is this guy? This guy is really x times y to the negative 1. Okay, so we're going to do the product rule of this guy right here. So what's the derivative of x is 1. So we have y to the negative 1 plus, we keep the x, and we're going to do the derivative of the second guy, which is negative 1 y to the negative 2, that power goes down, times dy over dx. Now, you're like, what do I do now? This is really weird. I have this weird dy over dx in my value. I have 1 over y plus, or negative, sorry, minus x over y squared, but I still have this dy over dx. What do I do? What do you know dy over dx is? Look back to the first derivative. It's x over y, which means the second derivative is really 1 over y minus x squared over y cubed. That is my second derivative. And let's say they gave us a point here. Let's say they said when x is equal to 0, x is equal to 0, y is equal to 2. Well, what would be the slope at that exact point? You could plug those values in and find, obviously, the slope of the second derivative. Okay, the slope of the slope, the slope of the slope. And so you can see this implicit function right here is able to give us calculate the second derivative. So that is calculating higher order derivatives in calculus. First derivative and second derivative, both regular and implicit.